Okay, we have treated power amplifiers in previous sessions in single-ended topologies. So it was based on common source topology. We have mentioned, we have discussed and analyzed how to bias and how to choose device size and how to treat the parasitics. However, there are some advantages for using symmetrical designs. We have discussed it when we discussed symmetrical LNAs or balanced LNAs. We call it even differential LNAs. There's some difference between LNAs and PAs because we don't want to use a current source for PAs because it will reduce our power delivery. So we will just talk about symmetrical designs or balanced design rather than differential designs when we talk about PAs. But there are some advantages to go with symmetrical PAs. One of them will be, of course, doubling power out without increasing voltage stress on each transistor. And here we have a topology that actually has two transistors. It can be, of course, two cascade transistors or two cascade topologies that are driven differentially. But by using a balun, which is actually two transformers, and injecting the DC current right in the middle, we bias the two transistors. And we also use this balun for, as we will see later, for impedance matching. And also by using this topology with a balun, we are doing a differential or symmetrical to single-ended transformation, and usually the output will be single-ended. So the balun topology has many advantages, and in the next slides we will see how we really design output networks of power amplifiers, symmetrical power amplifiers using a balun. Analyzing baluns, we need to go back a little bit and remember basic couple inductors equations, and we can see these equations right here, so we can find them in many textbooks. And if we just need to be sure about the signs, we just need to look at the definition of direction of the currents, because there may be some differences between different textbooks, but for these definitions between the two inductors, these are the right signs. So these are the expressions that actually describe these two coupled inductors. And it is interesting for us because when we look at the balun, we see two sets of coupled inductors. So we will just have this couple and this couple. And here we have the output of the transistors that are driving them. And let's try to analyze this output equivalent circuit. So we have current source here, which is actually the output of the transistor, and we have another current source here, and the current that this current source is driving is exactly the same current or very similar to the current that the other current source is drawing. So if we have very similar currents between this side and that side, we can assume that the ground here is not really seeing any total current flowing in it. So if there's no current flowing into the ground, we can just get rid of it. And if we get rid of this ground, which is the point where we use the VCC, or where we inject the current, but now we just treat the AC or the RF performance. If we just get rid of this ground for the analysis, we can simplify our circuit to be that circuit, where actually in this circuit we have two inductors that are double in their value, and of course the mutual inductance between the two inductors is also double. So it will be just easier for us to analyze this circuit, to draw some conclusions in the next slides. Analyzing PA balloon performance, we go back to the previous slide and we use the expressions that we have introduced for coupled inductors. But for our case, we know that the inductors and the mutual inductance is really doubled. So we will just keep it here in our expressions. But also when we look at V2, which is the voltage across the output equivalent circuit, we can remember that it is equal to the load current times the load resistance in a negative sign. We can just see it here in the output. And we will use this expression to actually express I load in terms of the input current, the input differential current. And by doing that, we can express V1, the input voltage or the differential input voltage, in terms of IN, the input current, and then just drive the impedance Z1 of the input to the balun. So this is the differential impedance to the input of the balun. And it is very clear that it has a real part and has an imaginary part, and this imaginary part is not surprisingly inductive, and it's very tempting to try and resonate it with the series capacitance. However, practically we cannot do it, because if we will put series capacitors, we will just block the DC current, and that's why we cannot really tune this circuit serially. So we have to tune it somehow, get rid of the inductive behavior in a parallel way. So if we want to do it in a parallel way, instead of using impedance, we should use the expression of the admittance, and this is what we are doing here. So we have Y1 is the admittance of the differential admittance of the input. And of course it also has a real part and an imaginary part, and by using the relative inductances and the K factor. Okay, K factor is actually the mutual inductance divided by the square root of L1 times L2. We get a more complicated expression, but it will be useful to follow this expression to draw some conclusions in the next slide. Our goal is really to tune out the imaginary part and keep a real part that is the optimal load that these transistors want to drive, or that this optimal resistive load will be the load which will optimize power out from these two transistors. We have just derived the input differential expression for admittance, and now we want to draw some conclusions and get some design conclusions on how to design this inductor. And for doing that, we just want to have one inductor in the expressions. And so we will use L1 equals A times L2. So A is a constant, but if we dig a little bit and go back to textbooks, this A is actually n squared, where n is the ratio between the turns of the two sides of the transformer. So it's actually a physical parameter we know from transformer theory, and it simplifies our expression to be this expression. It's a very long expression, and if we just want to make sure that we didn't make any wrong assumptions or mistakes in the way, we can just put the coupling factor, just use the coupling factor as a theoretical one, which is the optimal or the best coupling factor we can get between these two inductors. And then we get to this very known formula of 1 over A, which is n squared times the admittance. So we basically go back to textbook results that we know. And with this expression, we just know that we have the real part, which is the conductance. We want to choose the conductance such that 1 over the conductance, or the output resistance, will be exactly the optimal resistive load we want to see to drive maximum power. So this is the expression for our optimum. We can choose here L1 or L2, the inductances, since we are left with L2 and A in this expression. We just choose physical values for L2 and for also for K, because we cannot really get K of 1 in physical design. So K's of 0.7, 0.75 or down to 0.65 are more realizable physically. So one can choose the K factor, the L, and the ratio between the turns of the two sides such that our optimum will be achieved. And once this is done, once we choose the right parameters to really get our optimum as the equivalent output resistance, the differential output resistance, because we have two transistors that are actually driving this impedance, we are still left with an imaginary part that has this size, and we just need to tune it with a parallel capacitance that will actually eliminate the imaginary part from this impedance and will leave us with the only optimal resistance. So this will look like the matching circuit in AC. Of course, we have neglected here the DC biasing that we saw in the first slide, but it's actually a good way to describe output matching with a balloon on symmetrical PAs. In the next slide, we will see an example that will actually take us from this very complex world of long expressions and do a simple analysis to show how this is really effectively helping us in design. In this slide, we will cover an example of balloon matching. It's totally passive example, but we are touching the challenges introduced by designing the output balloon for this symmetrical PA. And so for this PA, we assume that we need an optimal differential load of 40 ohm. And we assume that the coupling factor will be 0.7, which is a reasonable assumption. The load is usually 50 ohm, the single-ended load. So we can see it here as a 50 ohm load. And we want to match this circuit for this frequency, which is around 3 gigahertz, as we can see here. And if we choose L1, the input inductors, as 0.47 nanohenry, which is a reasonable size to be implemented on RFICs. And L2 would be chosen as 2 nanohenry, and we can see that there's actually, it's about ratio of 1 to 4, and this is actually means the turn ratio will be 1 to 2, because A is actually n squared. And if we add C-tune of 3.68 picofarad by following the expressions we have developed in the previous slide, we will find that this system actually has a resonance very close to 3 gigahertz, where at this resonance, the real part, where we can see here, the real part really takes the value of 40 ohm, which is the value that we wanted to introduce to the transistors at the resonance frequency as the optimal load, and the negative and the imaginary part in blue here is actually zeros at the same frequency as we have calculated before. So by using this design, we have matched the output of the transistors in a way that we achieve the optimal differential resistance, and we have also biased both transistors, and we have taken a differential or symmetrical design and transformed it to a single-ended design at the output on the antenna. So far we have covered many aspects of PA design, and we are summarizing now what we have learned in the previous sessions. So we know that there's an optimal resistance where this output resistance, the transistor or the power amplifier can deliver maximum power to the load. And this optimal resistance is derived from the VDD and the DC current and the IDVD curves of the transistor. Also, the device size must accommodate the current needed for delivering maximum output power. We have talked about gate biasing that should support nearly constant GM over input voltage in such that linearity will not be degraded, and input voltage swing will be symmetrical as possible around the bias point. Then we have introduced output capacitance, which will always be there, and it's very significant with the power amplifiers, and it's always part of the output matching network. Cannot be neglected. We have to account for it and tune it out in different ways. We have described two of them. One was single-ended, the other one was differential, but it has to be accounted for in any PA design. We have mentioned parasitic source inductance, and we don't have good ways to really tune out this inductance. So the only effective, not the only, but the best way to effectively reduce the effects of this inductance is to minimize it by either paralleling wire bonds to ground, making the paths as short as possible, but we have to minimize this inductance. This inductance will really cause also stability issues that can be analyzed by using the terms or the expressions we have covered here, which is very different from the case it was with LNA, that this inductance was actually helping in stabilizing the circuit. Here it's a very non-stabilizing element in the circuit. So it degrades power out, it degrades stability, we should just minimize it. And then we have touched symmetrical design. We have covered some design perspectives, design aspects of balloons as a DC feed network and also as a load impedance transformer. Thank you for joining me to this session about the symmetrical PAs. This session has concluded our treatment of power amplifier design. Hope you can join me for the next sessions about mixers and voltage controlled oscillators.